So, just for the benefit of this, Becca, this video is just going through the uses of topological optimization and the ideas of what it's for. What we'll do on this one is we'll use SolidWorks as an intro for it. Many different ways that people do this. What a lot of people will do is they'll take the design and go into ANSYS, use Topilogical Optimizer. Then once you'll see this process, once it goes through ANSYS then gives you recommendations of what needs to be cut away. They then take the part out of ANSYS, put it back into the CAD system, and then modify it, and then put it back into ANSYS again. You kind of look, and you kind of sit there and go, well, could I not just do the topological optimizing in the CAD system, then put it into the FEA? And that's how I personally approach these things. So we're going to start off with something nice and juicily simple. So, where have you gone? Where have you gone? Are you there? Yep, for some reason you've... Can you still hear me, Becca?
I can.
Oh, just double checking. My screen went a bit funky then. I wasn't sure if I'd turned you off.
Still here.
Sweet. Right. So let's just aim at this as something that is the most nerdiest thing out there, and I personally love it. I think it's amazing. Shelf bracket. And I know everybody kind of looks and goes, well, yeah, but it's just a shelf bracket. But an example for topological optimization for shelf brackets is amazing, because it really does show you what this process can do. And I do need some geometry. Really, what I should have done is drawn this up before we actually got into this, but it doesn't matter. It won't take long, because it's nice for me to just display this to you and give you an idea of how this functions, because at least then what you do is you... Hang on a minute, why am I doing that? At least then what you do is we got you, make you equal. There we go. Right, so what we're going to do is we're going to assume that this bracket is going to be held on this. Well, this is obviously going to be taking the load, and this is going to be held against the wall. And what I actually want to do is I want to get into a position here where I can remove at least 60% of the material that's there. What the system will do is it will run it through loads and loads and loads of examples, and it will look at areas where material is totally redundant and where I can actually look to optimize key areas. And as silly as it sounds, this simple wall bracket will end up being something that's really useful. So let me first just go to the desktop, and I'll just stick it on as wall bracket. Click OK. Now, have you any questions about that at the minute, Becca?
No.
Rocking. So I've got to stick some material into this, so let's just do it out of something that's a little bit more interesting. So we'll do it out of... It's funny when you're randomly making some stuff up, you kind of sit there and go, but what do I want to make it out of? Like it matters. Oh, I know what we'll use. We'll use an ABS. Nice steady ABS, nice operational behaviours on it. And now we've got an ABS bracket. Now you've got to remember, using topological optimizing, you do skew a lot of your manufacturing options. In fact, you're going to see. So now, if I go to add-ins, oh, SolidWorks simulation is already turned on. So I'll go on to simulation, new, study, design study. We'll go and do a topological study. Yeah, select the body. Look at that. Hang on a minute. Give me that. Select the single body. Right. So I'm going to confirm that. So there's the wall bracket. It needs, as ever, like any simulation, it needs fixtures. So let's go to constraints. Just looking at what to actually. Come down here, I'll go fixtures. See, they've renamed everything up here. It just irritates me. So I'll just go fixtures. And what I'll do is I'm going to go fixed geometry. Granted, for this example, it is very, very clumsy what I'm doing, because really, if you think about it, we'd need a hole, wouldn't we, to actually act as the mounting point. But for what I want to do here, it does show that process that it goes through. So then I'll go loading, force, and let's go. I mean, it's ABS, so I'm going to go 150 newtons. Maybe, well, I'll go more afterwards, but this is a good start. Now, you see here it's got goals and constraints. I'll work down here, I prefer this. So what I can do is if I click onto here, this is the goals and constraints. So if you look, set goal, best stiffness to weight ratio, minimize maximum displacement, minimize mass. Let's just go for mass. I want to minimize the mass by, I said 60%. So what this will do now is it will ignore the displacement of the component sets. It will ignore, it won't take it to failure, but it will try and find as much redundancies as possible. So when you look onto here, you can actually put out your factor of safety. You can put on straight. Now this is, ironically, this is actually one thing that I do quite like. So you can say, do not compromise a factor of safety to it. If it compromises it, cancel the simulation. With frequency constraint, you can say if there's any compromising of the component under certain states, then do it. Even displacement constraint, you can say don't allow it to move more than 10 millimeters or something like that. But for this, just because we're going to do the first run of this on the mass, if I hit run, for maximize mass goal, select at least one or more constraint for feasible results. So apparently I've got to put a constraint on. Brilliant. Okay, so let's put that on, and then let's go to factor of safety, and don't compromise to a factor of safety of 1. Let's try that. Oh, and it's still very happy. And we'll go displacement, and 2 factors, okay. Oh, it's the yield. Damn it. Okay. What it's actually done, because I chose ABS, it's not happy with me because I chose that as a material set. So let me just go to here. Can I edit from here? Mass properties. Okay, I'm gonna have to change my material. I'll do it for something else. I'll make it out of steel. I'll do it out of a 1060 alloy. I know all the materials are there, that's all. So I'll come back in and let's go back onto here, and we're going to go 60% removal, reduction in mass by percentage, and is that going to let me do it? Yes, it is. It's just because it wasn't happy with me using ABS. A lot of people don't like to put in all the values to ABS because nobody wants to be the person that says, yeah, that's wrong. So from here, preserving regions. If I click onto a preserve region, what it's actually saying is, tell me the areas that you need to keep. Well, I know I need to keep the area that's going to be attached to the wall, and I also know I need to keep the area that is going to be holding up the plate or whatever it is that we're holding against. And I mean, if you were quite anal with it, you might want to say you want to keep these plates as well for aesthetics. But what we'll do is we'll drop them off for the minute. Say, look, preserve them regions. Then manufacturing controls again, we can say specific demolding direction, or make sure a specific thickness, or activate on a line of symmetry. So when you go on to activate under a line of symmetry, you can imagine what it's actually doing is it's looking for a plane to operate around. You can go 1/8 of a symmetry, where you can choose different planes to say that if it's this value on one side, it needs to be the same value on another. I'll show you what I mean. If I come onto here and then I'll make this a mid-plane extrusion. So I make that mid-plane like that. And all that's done is just shift that key point of axis, and it also makes my life easier when adding a specific symmetry plane. Now I put that on there just to make sure that whatever is produced from this, it is symmetrical. Just because nobody wants a shelf bracket that looks like it's been, well, thrown together by a 5-year-old. Symmetry is an incredibly important thing when it comes to aesthetics, or for any types of approach. If something's not symmetrical, people do not like it. Right, so let's create a mesh. The thing is this meshing procedure, as opposed to what you've seen on something like ANSYS, is very, 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 very basic. But the beauty is with this is this is not really an FEA tool. This will just run through your sim and offer you design modifications. You make them design modifications, and then you move to something bigger. You definitely don't stay with this. You move to something like ANSYS. You put it in there, and then you test it properly. And then if it starts to fail, you know to start making modifications from there. Right. So run this study. And now we wait. In fact, hang on a minute. Let's allow you. Let's allow you. So you see here, show static frequency and running order dialog. If I do that, it's going to give me convergence graphs as we're going through. So what I'm going to do for the minute, because it is going to take quite a few minutes to solve, I'm going to nearly forgot to put that one on. Right, so what you can see there is you've got recommendations, must keep through to OK. And it's an interesting thing that it's actually produced. What it's done is slim down the entire area. Now, what a lot of people do is they'll take this and they'll create a smooth mesh file. And some people just go straight to 3D print. So, for example, if I right click on here, then go export to smooth mesh. Current configuration, active, then OK. So what it's going to do now is going to generate a smoothed mesh version. And that's it. And then everybody looks and goes, well, what's that good for? If I come back across, I'm going to hide that. That is the actual part. Right? Now, what a lot would do is you can, if I suppress that completely, just suppress that, I can go to, I can output this directly as a different type of file. I could go for a step file. If I was going to print it, I could just go 3D print. So I'll go desktop, go to 3D print, click OK. And to show you what I mean, a lot of people will go straight into Cura. Any minute now. Apologies, it's still running and still running and still running. So you look, this will then go into, this can go straight into Cura. So a lot of people will just go straight from there and then they'll insert it directly, like that. Where that then can easily be moved towards manufacturing. So you can just print it outright. And loads of people have done this. It's crazy the amount of people that have done it. But what's the most important thing here is that the decisions that this system's made are actually based on the material that you've used. Now, the reason a lot of people do it is you must admit, when you look at it, it does look quite organic. It looks like it's part of a creature. But all it is, it's actually topological optimizer. It's gone through areas that aren't needed and it's trimmed key areas for it. Now, if you're wanting to use this as a key component to influence your design, what you essentially do is you turn your design back on and you turn that back on. And then if I make that transparent, change to transparency, right, so you can see there, that's what it is. Now, I've never actually tried subtracting one from the other, but that's not really the case of what I want to do. If I want, it tells me all sorts. It tells me how much I can trim away. It tells me where areas I could keep. And an interesting thing with it is you've got a common arc here that's occurring. And what I might do, for an example, in this case, if I went to start, and then let's just go for new, let's do a sketch. One thing I can see straight away is we have a common shape to be cut out. So what I might want to do is start cutting these out. Or, let me see, can we convert entities? Will it let me convert entities? Oh, obviously not. What I can do with it is go to a spline, go to here, to here, to here, and then I can, I mean this is me brutally doing it, but I can trace around this point. And then as I trace around that point, this then influences exactly which way I'm going to do it. Now, if I'm not happy with how this is going to cut out, which I don't think I will be, but if I'm not happy with how that gets cut out, I can actually modify it even more. But if I go, I'm going to do a cut, sorry. So I'll do a cut through all on both, and OK. And then what it does is it gives me my first thing to think about. That's the first area that I've chopped back. And now I've got pockets, huge amount of pockets here that I could start to remove. What I then want to do is look to cutting these bits back. Now the thing is, the way that this is designed and the way that something like a hip is loaded, it wouldn't end up looking something like this. It would end up looking a bit more skinnier, if you will, on key particular areas, and then we could modify that even more. But I think what the first thing is for you to do is to establish geometry, because we can do millions of things with this. It's like the graphic itself. I can export that and put that straight into ANSYS and test it in that condition. So in fact, let's give that a go. So if I get rid of that and get rid of that, so this is just like that. So if I go to ANSYS, just get rid of that. If I go to ANSYS, onto Workbench. Sorry, it's just taking a lot longer than I thought it would. So, now you know and love ANSYS by now, don't you, Becca?
Unfortunately, yeah.
So I'm going to import geometry, browse, and I'm told ANSYS actually will import. Look at that. STL files. Beautiful. Beautiful. So if I go to fine, whatever, because Space Claim is NURB orientated, it allows you to do it there. Oh goodness. I have 54 emails to respond to before the end of the day. Fuck me.
Sorry, none from me.
Yeah, last year they were from you every day.
I was the 54.
I had its own folder called Becca. I didn't, but you know.
It wouldn't surprise me.
Right, so now this, I mean, I give a lot of crap to this piece of software, but this is straight in there. It's instantly converted it to something I can use, and it's quite nice. I do quite like it for stuff like that. Now you see there, it's coming as faces. Now what I want to do is I want to convert it to a solid. Let's merge all the faces. Yes. I'd say 5, 4, 3, 2, 1, but let's face it. 10, 9. Oh, look at that. Oh, I swear to God, look at that. I can tell you're not as impressed as I am, but I'm impressed with that. Right, so that's now.
You know, you said it looked very organic.
Yeah.
I keep looking at it and going, it looks very much like bone.
I think that, doesn't it? Doesn't it look like a bone?
It does look like bone.
And you see, this is why a lot of people are seeing this tool now and saying, "Fuck, have we just missed this for years and just not looked at it?" So what you'll find now a lot in medical development, especially for implants, things like that, people are using topological optimization to, in essence, make it so that the body likes the geometry better, so it's not a painful process of transition. And you kind of look and go, I understand that. That makes sense. So let's just jump out of there. Look at that. Look at that. Are you impressed? I'm impressed. So I'm then I'm then going to right click on that geometry, and you know this process. Let's transfer to something new. Let's go static structural. No. Fine. Let's drag a static structural. Connect you up to here. You see, it wasn't that hard. It really wasn't that hard. Right, so let's go back again. And now, what this allows me to do is to go through ANSYS and use its absolutely phenomenal tools for meshing. And it allows me now to have that freedom of a tetrahedral for quadratic meshing. I can choose as you know, you can choose your node, your edging. There's so much more freedom that I've got here, and this is what I meant. So you kind of let the little CAD system give you a recommendation, and then you run it through something serious like this. And it's a good job I've recorded this, because I must admit, if I'd have looked at this for the first time, I would have forgotten how to draw. So, wait for it.
Can't wait to attempt this through Horizon.
Oh, wait! Don't start. I can hear the judgmental aspects already.
We're already trying to use ANSYS through Horizon at the moment. It's not as complex as this.
Oh, really?
It's gonna be fun.
You're gonna have so much fun. So much fun.
So much fun.
Well, we can always use console if you want to use that one.
What's that?
No, you know what? No, we can't because it's not got any CAD module attached to it. It's MATLAB's version of FEA.
Alright, okay.
Here it comes. And there you go. It's still bringing it in. Is it brought it in? Are we in? Are we not? We are in. We're in. Okay, so look onto there. Let's look at meshing. Wow, this is going to be a beast for meshing. Let's just generate a standard mesh. Let's see what it does. And let's run for a simulation. I think we went 200 newtons, didn't we? Did we go 200 newtons?
150.
Was it 150? So I'll go by that first. Let's go by component set. And then let's go by minus 150. And then let's run it. So this is our custom shelf. So let's just go stress. We'll just go equivalent stress for this. And let's go value results. You're right, it does look like bone. And as you can imagine, the highest concentrated area is at the top. Interesting though, look at that, right? We've got an equal force moving entirely across it. And when you actually scope yourself around, the force is at midpoint all the way around it, around the actual, if you will, bony edges. So it kind of does show that the process that the system was using is very good. If we look at displacement, let's go total. And you look on there. Actual movement in meters to the power of 7. So what's that? 4 mil? You think? You ain't. No, it's even less, isn't it? That.
Yeah.
But that's crazy. It's but it just shows that as a bit of kit we could probably put 150 on there, not a problem. But I hope what it kind of does show you though is as a tool, it is pretty amazing what it can do. And something like this, again, something like this does mean that everything that you've got from this point is only usable as a print. So this would you be taking the benefit of looking at different printing methods. And obviously, if we're looking at a material, a titanium material for a hip replacement, I mean, I know there's not just titanium, but it does really cone that range of materials that we can choose down. So yeah, the best process from this point now, Becca, find the geometry. Get a piece of geometry. Once you get that geometry, set up the bog standard simulation, and that is trunk hitting against the joint, which is hitting against that leg interface, and then let's just get an idea of what type of force is going to be running through it. Once we know the forces that have been translated through the entire assembly, then what we can do, isolate each component and then run optimization on each component, reassemble it, and then run that simulation again. If you get me? Do you get me?
Yeah.
That was my thought anyway. I don't know what you think.
That seems